The topic of this video is the optimal longitudinal force distribution and CG. This is part 6, single-wheel drive vehicle. Let's get it rolling. Hi guys, in this video I will explain optimal longitudinal force distribution and CG, part 6, single-wheel drive vehicle. The contents will be a quiz, the maximum acceleration of rear-wheel drive. Subtitle will be a governing equation, a practice with Excel sheet, graphical explanation, and the different friction coefficients. The same explanation that will be repeated for the front wheel drive. And then I will give you the answer to the quiz, and finally conclusion. Here is a quiz for you. Which of the following statement is right? Number 1. Maximum acceleration is not relevant to CG location. Number 2. Maximum acceleration is relevant to tire friction coefficient. Number 3. Maximum acceleration has the same value at both front-wheel drive and the rear-wheel drive if the vehicle weight is the same. All the discussions by now are about the all-wheel drive vehicle. In this video, I will explain the single-wheel drive vehicle. Let's think about the rear-wheel drive vehicle first. Governing equations are the same as those of all-wheel drive vehicle from the equation A1, A2, A3, and A4. And from the Newton's law, we have the equation A5. In the rear-wheel drive vehicle, 2f sub xf is equal to 0. Then we obtain the equation A6. From the equation A6 and A4 here, we can get the equation A6. Arranging the equation A6 about the ratio of acceleration A sub RWD to gravitational constant G, we can get the equation A8. When the friction is large enough, the front wheels lose their ground contact when F sub ZF is equal to 0, which is equation B1. On the other hand, we have already obtained the equation A1 in the previous explanation. Substitute 0 for F sub ZF of the equation A1, we can get the equation B2. Again, on the other hand, we have already obtained the equation A8 in the previous explanation. B2 represents the tilting acceleration, which means front wheels lose their ground contact. And the equation A8 represents the maximum acceleration allowed by the tire friction. This is a tire friction coefficient mu here. The maximum acceleration will be smaller one of equation A8 or B2. When A8 is equal to B2, equation A9 can be obtained. Arranging the equation B9, we can get the equation B10. We can obtain the equation B11. Substitute L minus L sub F for L sub R, because L is equal to LF plus L sub R. The value of A8 and B2 are the same when L sub R is equal to tire friction coefficient mu multiplied by CG height h, or L sub f is equal to L minus tire friction coefficient mu multiplied by CG height h. Let's make the Excel sheet to draw the graph of maximum acceleration depending on the CG location of the vehicle. In the Excel sheet, A is the same notation as A sub RWD. The data in the red box are the same one as those in the previous videos. We put the data in the Excel sheet as shown here and type the equation, this equation, in this column. The ratio of A to G. Then we are all set to draw the vehicle characteristic graph for maximum acceleration using these two columns. Here, L sub f divided by L and acceleration A divided by gravitation acceleration G. We will save this column for later use. Using the Excel sheet, we can draw the graph with the data in the red box for rear-wheel drive. Horizontal axis is the ratio of L sub f to wheelbase L, and the vertical axis is the maximum acceleration of G unit. Then the equation 8 can be drawn as a straight line with the slope of this much. Here, most of road vehicles have their CG locations from point 4 to point 6 of the ratio of L sub f to wheelbase L. Two vertical blue lines represents the point 4 and point 6 of those CG locations respectively. When the friction coefficient mu is equal to 1, for those two cases of CG locations, the maximum acceleration is 0.47 G unit when the ratio of L sub f to L is equal to 0.4, and 0.71 G unit when the ratio of L sub f to L is equal to 0.6. To help you understand the maximum acceleration graph, I will show you the three kinds of friction coefficients, 0.2, 0.6, and 1 in one place. The vehicle data are the same. Then we can calculate the maximum acceleration from the friction equations A8 for the three kinds of different friction coefficients, 0.2, 0.6, and 1. In the other way, we can also calculate the maximum acceleration from the tilting acceleration equation B2. The achievable maximum acceleration is the smaller result value of the two equations. In this graph, a thick yellow line shows the tilting acceleration. Vertical line 1 shows the reference line for the case of ratio of L sub f to L is equal to 0.4. And the vertical line 2 shows the reference line for the case the ratio of L sub f to L is equal to 0.6. Two equations, friction and the tilting acceleration, has the same values at the point 3, 4, and 5, when the ratio of L sub f to L is equal to 1. All the weight is at the rear wheels and no weight at the front wheels. In this case, tiny small acceleration makes the front wheels lose their ground grips. Therefore, the maximum acceleration is equal to 0 because no ground grips at the front wheels make the vehicle lose its steerability. When the ratio of L sub F to L is equal to 0, all the weight is at the front wheels and no weight at the rear wheels. In this case, friction force is equal to 0 because no vertical force cannot produce horizontal friction force. Therefore, the maximum acceleration is equal to 0. As you can see, a yellow friction equation line has negative slope, which means tilting acceleration more easily happen when the vehicle CG moves to the rear axle. On the other hand, friction equations have the positive slope like this manner, which means friction forces are increasing when the vehicle CG moves to the rear axle. In the case of friction coefficient 1, maximum acceleration can be obtained by equation A8 when the ratio of L sub F to L is less than 0.84 in this area. But the equation 2 should be employed when the ratio is larger than 0.84 in this area, because the front wheels are lifted by tilting acceleration. The same thing happens in the case of friction coefficient 0.6 and 0.2 at this point, as shown in the graph. From now on, let's think about the front-wheel drive vehicle. Governing equations are the same as those of all-wheel drive vehicle from the equation A1, A2, A3, and A4, and A5. From the Newton's law, we have A5. Here, 2f of xr is equal to 0 for the front-wheel drive. Therefore, we have the equation C8. From C8 and A3, we could get the equation A9. Arranging the equation A9 about the ratio of acceleration A sub RWD to gravitational constant G, we can get the equation A10. For the front drive vehicle, let's make the Excel sheet for the graph of maximum acceleration depending on the location of center of gravity of vehicle. In the Excel sheet, A has the same notation as A sub FWD. The data in the red box are the same one as those in the previous slide. We put the data in the Excel sheet as shown here and type the equation A10 in this column. Then we can draw the graph using these two columns. It's a column for the ratio of L sub F to L, and the column for the ratio of A to G. Using the Excel sheet, we can draw the graph with the data in the red box for front-wheel drive in the case that the friction coefficient is equal to 1. Two vertical blue line represents the 0.4 and 0.6 of the ratio respectively. For those two cases of CG locations, maximum acceleration is 0.51 g unit. In the case of the ratio is 0.4 and 0.35 g unit in the case of the ratio 0.6 here. To help you understand the maximum acceleration graph, I will show you the three kinds of friction coefficients, 0.2, 0.6, and 1, in one place. The same way as before, in the case of rear-wheel drive, the vehicle data are the same. Then we can calculate the maximum acceleration from the friction equation A10 for three kinds of different friction coefficients, 0.2, 0.6, and 1. In the other way, we can calculate the maximum acceleration from the tilting acceleration equation B2. The achievable maximum acceleration is the smaller result value of the two equations, A10 and B2. In this graph, a thick yellow line shows the tilting acceleration for the front-wheel drive when the ratio of L sub F to L is equal to 1. All the weight is at the rear wheels and no weight at the front wheels. In this case, even tiny small acceleration makes the front wheels lose their ground grips. Therefore, tire cannot transfer the engine power to the ground, and the maximum acceleration is equal to 0. When the ratio of L sub F to L is equal to 0, all the weight is at the front wheels and no weight at the rear wheels. In this case, friction force is equal to 0 because no vertical force cannot produce horizontal friction force, and the front wheels lose their steerability. Therefore, the maximum acceleration is equal to 0. As you can see, yellow friction equation line has the negative slope like this manner, which means a tilting acceleration more easily happen when the vehicle CG moves to the rear axle. The friction equations also have negative slope like this manner, which means friction forces at the front wheels are decreasing when the vehicle CG moves to the rear axle. Did you hit the answer to the quiz? The answer is number 2. Maximum acceleration is relevant to tire friction coefficient. Here we have some conclusions. The achievable maximum acceleration in the rear-wheel drive is the smaller one of the two equations, the friction equation A8 and the tilting acceleration equation B2. The achievable maximum acceleration in the front-wheel drive is calculated by the friction equations A10. I explained the importance of lowering CG height with practical example. Lowering CG height is the only way to improve both of acceleration and braking performance. And you can find the explanation on the variation of optimal longitudinal forces distribution for different CGs. I recently explained the optimal longitudinal front-rear acceleration and the braking force distribution together with the constant friction lines. In the next video, I will explain the optimum longitudinal force distribution, part 7, especially about the minimum acceleration time from 0 to 100 km per hour. See you at the next video. Goodbye, guys.